some crazy speech on math. What is it? Are you stealing slides? What? Who's got it? What? What the fuck? Oh, right. Okay. Okay. We'll start with. Hi, Bill. We'll start with the basics. All right. Do you guys know what big O notation is? Like everyone. Is there anyone who doesn't know? All right. Great. That's great. All right. Do you guys know? This is going great. Do you guys know greatest common divisor and the Euclidean algorithm? Everyone? No? Okay. I can do Euclid's really quick. Okay. Euclidean algorithm. You get. Everyone knows what the greatest common divisor of two numbers is, right? Okay. The Euclidean algorithm does that in log base 10 n. That's big O notation. I glossed over that before. And the way it does it is you take two numbers, let's call them A and B, and the bigger being A, and you do A modulus B, and then the remainder goes into R, and then you shift those over so B becomes A and R becomes B, and do it again, and you keep doing that till R equals 0, and when you're done, B is the greatest common divisor. It's really fucking fast. Like log base 10n, right? Great. Oh, modular math. Do you guys... I want to be able to show this to you.
Matrix. Ask if anybody...
What? Yeah, I'll pass it around. What?
Ask if anybody just has a really long RCA patch cable.
Does anyone have a really long RCA patch cable? Nick Farr wonders. This is great. Okay, well, modular math. Do you guys know what, like, if I were to say 27 is congruent to 3 modulo 12, do you guys know what that means? Okay. It looks like 27 and an equal sign with 3 bars, and then 3 and then a parenthesis and then modulo 12, and it's written in, like if you're writing in C, it would be 27% sign, 12 equals 3. It's basically like, think of it like an if-case statement. And I really need an overhead for this. Because the next thing I was going to go over was Euler's totem function. And it looks like it's the Greek character phi. All right, someone try and make that work or do something. I don't know what the... All right, hey, did you find DT?
Yeah, I found DT.
So what's up?
Supposed to be getting an overhead over here.
All right, well...
Somebody explain what the possibilities are.
All right, well, they do whatever. You guys use your imaginations, okay? What? Does anyone have an RCA female to female gender changer? Because Nick Farr wants one.
Yeah, why don't you sit in a chair here, do your scribbling, bounce back up on stage? I mean,
someone figure something out. I don't care, but on what though? What are we gonna write on?
One of the tablecloths over there.
I'm not gonna type latex.
Okay, so
Yeah, well, do you guys want to just, what?
the projector up?
To do what? Yeah, you do whatever you want. Move that shit around. I just want you people to see this overhead. That's all I want.
All right, set up a chair. Grab a tablecloth or something to give you a white background.
What?
You can bounce down this.
What do you want me to do with the 10-minute break? You want me to entertain you? Would you like me to sing? What? I can sing. Is that all you people want? All right, whatever. We'll skip over what's called a quantum bit, and all right. So there's lots of different ways to do that using physics and all sorts of other crazy stuff. But for the time being, just like whenever I talk about any quantum physics, just forget all physics and imagine that it's magic, because it is. And it is. And okay, first thing, superposition. A quantum bit, like, it can be a 0 or a 1, or it can be what's called a superposition, which is in between state between the two. And it's only a 1 or a 0 if it's it's only a 1 or a 0 if it's already decohered, which is making no sense right now because I don't have any overheads. Okay, so what's that? Couple minutes, great. What's up? What do you want me to do? Tell me. I can sing Peter Gabriel pretty well. It's a song I used to always sing. What do you want me to sing about? I'm going to sing about what? You guys are all talking. It's what? What? All right, I got a joke for you. All right, so this grasshopper, he walks into a bar, and the bartender's like, "Hey, we got a drink named after you." And the grasshopper goes, "Really? You got a drink named Lenny?" What's up?
Very delicate operation.
All right, is this a hacker convention or what? What's up? All right, well, we still have the problem that, like, I wrote these while I was really fucked up last night, so... All right, no, we're good. No, just don't die on that thing. You duck. Yeah, great. Okay. What? Wait, this is good. So there. Yeah. So what you got great timing. What? Are we going to do this thing or what? What?
It's better with this because then you can stay up here.
No, we'll do the over. Just plug that fucker in. All right, I'll start on this thing. All right. You guys can see that, right? All right. Going back to math all the way back. We glossed over Big O and all that shit. Euler's totem function, basically phi of n. It's the number of numbers that are between 1 and n minus 1 that are relatively prime. Do you guys know what relatively prime means? Okay, it's greatest common divisor. Yeah. Okay, and so that's phi right there. And then Euler also had a theorem, which is right there. If t and r are relatively prime to each other, and t's the bigger one, then t phi r is congruent to 1 modulo r. Which means basically, if you take t and you multiply it by itself phi r times and divide the result by r, you will always get 1. So that's all that says right there. And they're still doing overhead shit. So what that's used for is what in the? Oh yeah, no. I remember what I was doing here. All right, check this out. Hey, give me back that Euler's totem. Quit moving my stuff around. All right, great. Check this out. Die!
All right. Do this video stuff.
All right, great. Can I pull this mic off?
That's all the slack you got. Go.
Great. What the fuck happened to my note cards? Would you quit moving my shit? All right. Yeah, now I'm gonna have to actually speak, huh? All right. So. So we got the Euler-Stoden theorem, right? And this is what RSA is based on completely, basically. So we start out with that theorem right there in general, and like by just basic math, we can multiply it by itself on both sides, right? Like, do you guys, what time is it? Do you guys really want to see me derive this or not? It doesn't matter. All right, no, okay, that's great. The end product, just the RSA in general. All right, well, no, I'll do this fast. Yeah, just for you, Bill. If you guys don't know what I'm doing here, just stop me. Like, this combines. Alright, and you see how you can keep repeating doing this? Like, you just keep multiplying by t pi r, and since you're already doing it, since it's modular arithmetic, you can do that as many times as you want, and it doesn't matter because it's modulus, right?
The third line has to be a plus.
Where? The who? Oh, yeah, duh. Great. No, he's right. And, so, anyways, yeah, so you get that, right? And so you can keep doing that, and let's call this an S, and that's any integer, right? So that's like our first modification to that. And then the second thing we do is we've got TS drugs multiply both sides by T, just gives us mod R, and then like we can keep, well, okay, we got a times T here, times T at like exponential math, right? Great, right? Everyone got that so far? And then like we did before, we can keep doing that. We can keep multiplying T by both sides. And stop moving.
Move the overhead up.
Yeah. So we can keep doing that, and we can make this an E eventually. But really, the one we want is the one with the plus 1, because we can take T S phi r plus 1 congruent to T mod R. You still see that? Great. And we take that, and then this part right here is what we're interested in. So we take that, and we create a all right, great. We say P times Q equals that, right? And S phi R plus 1. So those are P and Q, which will be our two prime numbers that we generate a key with. So we substitute that in. And then from that we can get, let's get squeeze it down. Great, they're right here. Oh, over, right, great. Yeah, so there's there's your encryption, decryption algorithm, respectively, for RSA. Basically, RSA works on, if you don't know the basic principles, it takes really big, the product of two really big prime numbers, and using that in Euler's totem function, you can basically do the inverse modulus of, you can do an inverse modulus operation, which is crazy if you think about it. And the encryption does the normal modulus, and the decryption does the inverse modulus, and it makes it really hard to decrypt because the only way you can do it is by guessing P and Q, which also happens to be the Euler totem function of P minus 1 times Q minus 1. All right, whatever. So that's RSA. What's this thing? I don't want that. We'll go over this. What was I going to talk about? Oh, it really is quantum shit. All right, qubit. So I went over that a little bit. It's just a quantum bit. That's what it's called. Whatever, right? Superposition. Okay. With quantum bits, you can get... it can be a 1, a 0, or something in between. And the something in between is called superposition. And when something's in a superposition, it's got like a, let's say maybe a 75% chance of becoming a 1, and a 25% chance of becoming a 0. That's called a superposition. And it has to do with like the way quantum mechanics works. Like I said, it's magic. Well, I'll go to EPR state. EPR state stands for Einstein, Podolsky, Rosen. They're the guys who researched it. And that also has to do with entanglement a little bit. You get two qubits together, and you use a Bell state analyzer, and you check them out. And they will, you can get them so they're both in a 50-50 superposition. So it's got a 50% chance of becoming a 1 and a 50% chance of becoming a 0. And that's called the EPR state, when everything's got equal chance of becoming whatever. Which leads us to decoherence, which is what becoming is. When something's in a superposition, you can't read the data. The second you read the data, it will snap into one of the positions, 1 or 0. That's called decoherence. And like if you're in an EPR state and you read the bit, it will decohere to a 50% chance of being a 1, a 50% chance of being a 0. And using that EPR state, you can, also with the EPR, I glossed over this again, but the entanglement between the two qubits that you have in EPR, there's a control bit and the whatever not control bit, and when you read one, the other one will decohere to the exact same value based on what that is, and that's what entanglement is. And it's pretty crazy like that. Like, let's say I decohere, or I put two qubits in EPR state, and I give one to him over there somewhere, I give one to someone on the other side of the world. He reads his. The next time he reads his, it'll be the same value. It's like having two linked coins, and you flip it a bunch of times, as long as they're entangled. And you get a sequence of heads, tails, tails, heads, whatever. The other one will do the same random sequence. But anyways, with that you can create a controlled NOT gate, which is, if you don't know what a controlled NOT gate, that's the way it maps. You got your control bit. If it's on, it does a NOT to the second one. If it's not, it does nothing. And you can make every other type of gate that you need out of that. Yeah, any questions on that? Anyone? All right, no, great, that's perfect. Okay, so, what's all this? What's up? Where? Who? Yeah, go. Shout loud, please. His question was, are they teleporting with entanglement? No. The way those teleportation things work is they transfer the information using qubits, and they've still got to transfer entangled photons, which, it can only go speed of light or whatever. And it's like a mapping of the information, and it rewrites it. Does that make Right. Balls. What? Oh, he said, what? Why? Shut up. All right. So, any other questions on that? What? Go. Red hat person? There are a couple ways to do. Man, I'm not. Okay, well, there's a couple ways to do it. One way is you just read them with the Bell State Analyzer, and they entangle with each other. Bell State Analyzer? Something Bell made up? Does anyone have any? What's that?
Is that important to your talk?
No, it's not at all. That's. Oh, he's got information about Bell State Analyzers.
Actually, well, not the Bell State.
Oh, entanglement?
Actually, not the qubits that become entangled, it's the photons that become entangled.
Right, whatever. Same deal.
So that's probably what the confusion is, because when the photons become entangled, that's when the other side will
Right.
qubit will always be one place to actually read it and where you put it.
Right. No, you're right. But it doesn't matter for what I'm saying. Does anyone have any questions that aren't like physics related? Like, this is an algorithm speech. Okay. All right, great. So, what this is used for now, is getting to algorithms, which I kind of glossed over, is remember I talked about RSA and how factoring really big numbers. Does everyone understand that factoring the product of two really large prime numbers is a hard thing to do? Okay, just want to make sure. All right, Peter Shor, he made this fun little algorithm that will break RSA in 2 steps. Rawr. Basically, the way it works is you. What end did I use? I had a demo example with all the math done out already, but I don't have a calculator on me. Hold on a second. Keep them entertained. What? Keep them entertained.
Same thing. Choose what to do for one.
I got it. I'm good. Oh, that's even better. I just put someone's calculator in my mouth. All right. So, anyways. Okay. Let's say our n is 15, right? That's 3 times 5. They're both prime. It's really easy to do. Simple for us, right? So, the first part of the algorithm is you choose an a which is less than n. So let's say a equals 7, right? Then we create a function called f of x. I might have glossed over this also. With quantum computers, anything that you do with 1 qubit is like a massively parallel operation to everything else. So basically, you can, let's say you've got 2 qubits, 2 qubits entangled. You can do 4 operations at the same time on, it's 2 to the number of bits you have. So anyways, you can, and a superposition can store that much data also, 2 to the number of qubits you have entangled. So 2 qubits entangled can store 4, I guess, lines or superpositions of information. So what you do is, first you load up everything, or the superposition with all the numbers, all the way down or whatever, right? And you apply this function to all of them, which will give you, well, in case you need that, whatever. That's wrong. That's the way the math works. All right, I did them ahead of time. And what you want to do is, then after you do that, you've got this whole sequence in the superposition. And you can do what's called a quantum fast Fourier transform, which will find the period of repeated sequences here, which happens to be 4. Right, so r equals 4, which is the period. And there's actually an old number theory problem that's based on. And the fact that we just solved that in 1 step with fast Fourier transform. It's like X-ray diffusion, sort of. What we can do then is take the greatest common divisor of n and a to the r minus 2 plus or minus 1, which will give us, we put a 4 in there, 50 for the plus, 48 for the not, which gives us 5 and 3, which are the original dealers, right? Yeah, so, and you can do that with really big numbers and it doesn't matter. So as long as you got enough qubits to support all that stuff. So we've still got to make really big quantum computers for that to work, but you know, when we do, you've got you've got RSA broken. And so does everyone see how that fucks with RSA? All right. Then this other guy, Love Grover, he made himself an algorithm too. And his is for searching. And okay, basically he made a search algorithm that says, let's say you want to search sample space n. Normally you've got to search everything, so your average case is going to be n over 2, right? He can do it in square root of n, which is still in the same complexity class, but hey, it's faster, right? Like significantly faster. The way it works is, sort of do it up here. Let's say you've got yourself a, you got a 2-qubit machine, and those are your n's, or you know, whatever you've got in your superpositions, and it's a search algorithm. So you're searching for a specific item, and right. So let's say we're searching for like 3, right? Or 2, whatever. Start with 0. And so the way it works is, it works with probability amplitudes. Like I said, with like it's really easy to find it, anything in a quantum computer, but if you try and read the data, it'll destroy everything that you found. So it's like the find's really easy to do. It's just getting the data back out, which is the hard part. So find's easy to do. You found it, piece of cake, whatever. But you still can't see it yet. So it uses what's called probability amplitudes. Like I said, right now this has each one of these in EPR has a 1/4 chance of becoming whatever, you know, one of those when it decoheres. So I'm going to 0, 1, 2, 3. I'm going to sort of label and make a little graph here. 0, 1, 2 is actually 2, 3. They all start out like that. Then you can do you can invert the phase of the found one, really easy. Almost easy. Boom. So we inverted that, like that. That's an operation you can do pretty simply. Then, what's that? Where? Yeah, I should. Like I said, I did these when I was fucked up, so leave me alone. So, what was I saying? Oh, right. So this is the found one. You invert the phase, and then you do what's called an inversion around the average. So 1/4, 1/4, negative 1/4, 1/4. That gives us what now? Fuck, I'm wrong. These go all the way here. Because EPR... It's 1/2 per bit, whatever. So you got 1/2, 1/2, 1/2, 1/2, and the average turns out to be 1/4, which is what I completely missed. So the average is 1/4, right? So you find the average, and then you flip around the average. So like, how do I put this? Like this guy's here, right? What's that? Yeah, exactly. I just want to make sure people can see this. Right. So this one flips around to here, this one flips around to here, this one flips around to there, and this one flips around to there. And since we've only got a 2-qubit machine, we only have to do this once, square root of 2, whatever, one step. And now our found one has a 100% chance of becoming our found data when we read it and it decoheres, and everything else has a 0% chance. And like if we had more, like a bigger system here, we would have to do this approximately square root of n times, those 3 steps, the inverting around the average. But eventually everything else would go to 0, and the one that you had would go to 1, and you're good to go. So that's fine and great, like for searching a phone book, you might think, but like you've still got to put all that data into the superposition, which is going to take n steps. So it might, n square root of n. What's the point of that, right? But what this actually can be used for is, again, since we have massive parallelism of a quantum computer, we load up all the states with all the numbers 0 to 2 to the 56, and then we run a DES decrypt on all of them, and it's one step, so it's the same as one decryption operation, and you've got everything on, you got every possible decryption, and then you do a search for the plain text, and you filter it to the top, decoder your state, and you've got the plain text. So, yeah, basically, you can brute force anything in square root of n with this dealie here. Yeah, any questions on that? Shoot.
Is this a fairly new algorithm? Because I heard you ask that quantum computing helps for symmetric algorithms, but it only helps by reducing it by 1 bit the work factor.
No, this isn't that new. And Peter Shor's algorithm certainly speeds things up pretty quick. Oh, she was wondering if this was a new algorithm or not. Actually, recently he revised it, so it's faster now, I guess, or a little bit better. Did that answer your question good enough?
So it works. Symmetric algorithms can be broken as easily as asymmetric algorithms. Or about the
well, yeah, it's the same, yeah. You've got that one step, and then it's the search. So, it doesn't matter. You.
Yeah, so you're saying that this operation will in one step provide all of the possible outcomes of that key, and then you say you're going to do a search for plain text for the one that has plain text.
Right.
Now,
well, it's not this operation. Like quantum computers can do that just by stringing together controlled NOT gates.
but you're still, all these possibilities is still a very, very, very large number of different possibilities.
Right.
You're still having to search through all of those for the plain text. So I fail to see how this really is helping too much because they're still having this basically brute force of search on the plain text.
Right, it's still a brute force, but instead of a brute force of n, it's a brute force square root of n. What's a bigger number, 2 to the 56 or 2 to the 28? Yeah.
The thing is, it does all of the steps in one step.
Right.
Because it's not equal here when you're...
Oh, is that what you were asking? Yeah. Oh, right. No, okay, I see what you're saying. Exactly. No. When it does its stuff, when it's magic, right? When it does its stuff, it does it to every single thing at the same time. Every single item in the superposition at the exact same time. It's massively parallel. So you can have it, let's say it was something that normally takes like 5 minutes to do, right? And you're going to do it on 1,000 things. It takes 5 minutes to do. Okay? If you're going to do it on 1,000,000 things, it takes 5 minutes to do. It's the search that takes the time. Okay. Yeah.
We talked a lot about how quantum computers can help break encryption very quickly, and I know that you showed the first algorithm, but another thing is how quantum computers help encryption. The only example I've seen of that is we didn't talk about whenever the state isn't made and the whole thing collapses.
Yeah, that's coming up.
Oh,
Yeah, do you want me to go to that?
Well, I was going to talk about
I'll go to that.
Well,
You want me to go with that? I'll go right now.
Just one second.
Okay.
What about the phone stuff? You have a voice communication. If anyone tries to wiretap it?
Right.
Is there any type of storage type of encryption for
Well, just quantum computers are very delicate babies, and you don't want to be storing anything on them, really. Like, they got to put them in crazy underground places and away from electromagnetic radiation. Like, little disturbances will completely destroy them. Like, that's the way they do this stuff. The way they send something to an EPR state is they just shoot it with a little bit of electromagnetic radiation, and anything from the outside will completely fuck it up. It's 10 to... I'm going to go over this really quick, unless... Do you want me to go over quantum encryption? Or, okay. Okay. This is a BB-84. It's made in 1984 by Charles Bennett of IBM and Gaz Brassard of the University of Montreal. And, all right, I'm going to... Oh, I was fucked up. This is Alice and this is Bob, right? And so, Alice creates a random string of data first. Someone start shouting out ones or zeros. I'm hearing oh, damn. Okay, so Alice creates a random string of bits, right? And then all right, she's creating these in photons, and photons can be polarized. And these are the polarizations right here. That's the up and down polarization and the slashy polarization, and this one and that one. And the ones can be one of those, and the zeros will be one of those, right? So she knows what the polarizations are too. Let's just make these at random also, but make them match up. All right, so she knows the polarizations, and she sends these out over, a quantum communication channel, like a fiber optic or whatever, and Bob receives them. And Bob, he's got these two filters. One looks like a plus, and one looks like a multiplication symbol. And the plus lets through the vertical, horizontal ones, and the other one lets through the diagonal ones. So he creates a bunch of random, he at random, like randomly picks these things, a bunch of filters. All right, and the ones that work out great, they work out great. The ones that don't, you get some random thing, like maybe a 0, I'll mark it with a little red thing. Maybe you get a 1. Oh, who's calling me? So you get a 0 there. Hold on a second. Okay, so let me finish this up. Do you guys see what I'm doing here? This one's so long. All right. So I marked the little ones with the little thing in the corner, the ones that are wrong, but Bob doesn't know that yet. So then what Bob sends back is, Bob sends back the sequence of filters that he used, or analyzers is what they're called technically. And Alice uses these and compares them with her set of polarizations that she used, and then she tells him which ones were right. So he knows that this is good, or tells them which ones are bad. How's that? So they know the bad ones, right? And, okay. So then what they do is they use this sequence, the remaining bits, as their key. So, and if someone's trying to eavesdrop, all right, Alice creates all these bits with the random polarizations. If someone's trying to eavesdrop, first off, by reading the decoherence will destroy the data, but even if somehow they manage to figure that out or whatever, they've still got to use some random filters or analyzers to read the polarizations, and if they get the wrong ones, they're screwed. And then Bob sends back the analyzers, and it's really hard for the eavesdropper to figure out what's going on. I kind of glossed over that, but trust me, it works out that way. And if you use a one-time pad, everyone know what a one-time pad is? Everyone know they're unbreakable? Well, right, if it's totally random, like if it's a real one-time pad, it's totally unbreakable, right? Well, if you can figure out how to do that, and like nothing gets more random than superpositions, then boom, one-time pad, great. Yeah, okay, so any other questions, or do you want to hear more about, I completely skipped over complexity theory. Any questions? Someone there?
So when Bob said filtering back
Oh yeah, the eavesdropper can get that, sure. Everything that's sent through, you assume that E is always in the middle and can figure out everything. But even if she gets all the analyzers that were used, it doesn't matter because it's after the fact and she's already analyzed her stuff. So she's got, you see what I'm saying? Like it's a one-time operation, the analyzing the thing, so there's no way to, even if you've got that information, it's too late. Any other questions? I could understand 3 words you said. It was filter, results, and bad.
the rest yourself.
Right. But the important thing is you can't use them again because it's already been read. Okay. Anyone else? Questions? You there?
How long until we can do any of this?
Well, last I heard they had a 7-qubit machine somewhere. I don't know where, someplace in California in a fault line, something. I don't know. I don't know how it works. I'm not, what's that?
Nothing there to disturb.
Right. I got 5 minutes. All right. Any other questions? Anyone? Someone there raising their hand? Oh. No, you guys can both talk at the same time. A steel cage match? I'll arrange it. Okay, what's up? Yeah. Yeah. Right. That works for what? Well, no, not, no. One-way hashes, if you do a one-way hash, there's no way you're getting your stuff back otherwise, besides brute forcing it. No, that's why it's a one-way hash. It's more than a clever name. Well, RSA can because it's based on anything that's based on factoring the product of 2 prime numbers. What's that? Yeah, but then that has to do with quadratic field. What's up? Yeah. Well, it doesn't matter because anything can be brute forced with Love Grover's algorithm, just searching for the plain text. So, yeah. But that's not as fast, no, but still, it's... What's up? Right. Yeah, I know. It's the same complexity, but still, it's a lot faster. What's up? Yeah, it's still quantum computing. You're still using a quantum computer. All right. Anyone else want to say anything? Or all right, great.